Hello, everyone. Today, I want to talk about a breakthrough in artificial intelligence architecture that just came out from DeepSeek. It's called mHC, short for Manifold-Constrained Hyper-Connections. This is a foundational shift in how we build and train the most advanced AI models. Over the next few minutes, we'll explore what this innovation is, why it matters, and how it could shape the future of AI development. Let me start with the challenge that DeepSeek is solving. For years, AI researchers have known that expanding the width of neural networks, essentially giving them more thinking capacity, leads to better performance. There's a technique called hyperconnections that does exactly that. The problem? It breaks something fundamental called the identity mapping property, which is critical for training stability. As you push models deeper and wider, training becomes unstable. You get gradient explosions, representation collapse, and you have to apply workarounds just to keep training from falling apart. And there's another cost: memory overhead that makes it impractically to deploy at scale. So, what's the solution? DeepSeek's mHC framework reimagines how residual connections work. Instead of letting the network operate freely, which leads to chaos, mHC constrains those residual paths to operate on what's called a manifold. Think of it like a mathematical playground with guardrails. You get all the benefits of wider, more expressive networks, but with stability built in. It restores that crucial identity mapping property while keeping everything that made hyperconnections powerful. And it does all this while being practical to implement. Let's dive into how it actually works. At its core, MHC uses manifold projection to constrain the residual matrices. Those are the mathematical operators that transform information as it flows through the network. This keeps them in a safe, well-behaved region of parameter space. The network maintains multiple parallel semantic streams for each token. Think of these as different representations of meaning flowing side by side. The mixing operators that blend these streams stay mathematically well conditioned, which prevents the two biggest nightmares in deep learning: representation collapse, where everything becomes meaningless, and gradient explosion or vanishing, where learning signals either blow up or disappear. So why should you care? Here are the concrete wins. First, training becomes stable at depths and widths that would normally cause problems. Second, and this is important for practical deployment, you only pay 6 to 7% extra in memory and compute. That's a rounding error compared to the benefits. Third, empirical testing shows MHC outperforms vanilla hyperconnections on standard benchmarks. And fourth, it scales. We're talking about models with 3 billion, 9 billion, even 27 billion parameters and beyond, all training cleanly without the usual workarounds and compromises. Let me show you what the data actually says. DeepSeek tested MHC across multiple model sizes: 3B, 9B, and 27B parameters. Across the board, you see consistent, tangible improvements on key benchmarks. Compared to standard residual blocks that most transformers use today, MHC shows superior scalability. And here's what's really impressive: training stays stable. No gradient clipping hacks. No special tricks just to keep things from exploding. Clean, efficient training from start to finish. Now, why does this matter beyond academic interest? Because it changes the equation for building frontier AI models. For years, the assumption has been if you want better reasoning and better outputs, you scale up. You use more parameters, more data, more compute. That's expensive. NHC opens a different path. You can get stronger reasoning and higher quality outputs through architectural innovation instead of just brute force scaling. That means more efficient frontier model training. That means lower deployment costs. That means better performance per dollar spent. And strategically, this positions manifold-constrained residual connections as potentially the new default architecture for transformers going forward. So as we look ahead, mHC represents a foundation for the next generation of AI systems. It's stable, it's scalable, and it's practical. This is the kind of architectural innovation that compounds over time. Every future model built on these principles will be better than it would have been otherwise. Thank you.